Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to fill the gaps using Earth observation satellite data in Google Earth Engine platform and Python API programming. As you can see, the satellite data with daily frequency always suffering from the cloud impact and no data gaps, and also caused a lot of uncertainties in the estimations. But thanks to a statistical analysis and different techniques in the data science, we're able to fill the gaps and recover the missed data with a good accuracy. So, if you want to know how to do this procedure step by step using the Earth Engine and Python API, follow this tutorial. So, in the first step, make a new notebook in the Colab environment because we want to do programming in the Colab and make a bridge between Colab and Earth Engine. In the first step, we need to call necessary libraries to have access Earth Engine resources in the Colab environment. Start with EEE, import GEE map, and then import Xarray as XR. These are the essential libraries we need. And the next important library is XEE. If you search on the net about Google Earth Engine and XEE, you will find a GitHub page officially provided by the Google developers that allowing you to understand how to install XEE libraries in the Colab environment. What is the XEE? The XEE is one of the newest libraries in the Python that allowing you to actually convert Earth Engine image collection from the collection format to the Xarray structure. That is really beneficial for us because extend our capabilities in satellite data processing using Google Earth Engine platform. So here there is a detailed instruction how to import and how to use this library. But first of all, we need to install the XE library in the Colab. Let's do this through pip install XEE. Then import it as a single library into Colab environment. So once the installation done, in the next step, we need to make a bridge between Earth Engine and Colab environment. First, through the authentication, and then Earth Engine initialize the cloud project connected cloud project account that is connected to your Earth Engine. The project name equals to something, username for example, and the next one is UPT-URL, OPT-URL. In the instruction here, you can find the OPT-URL from the GitHub page. Just copy and paste it. To find the project name associated with your account, go to the Earth Engine code editor environment. Upper right in the corner, you can find your account information. Go to the project info, and here you can find the cloud project name connected to your Earth Engine and Google Cloud account. Just copy and paste it or type it like this. Every one of you has a single cloud project name that is not same with others. So now I'm trying to write it completely like this and then run this. So there is a typo mistake here. It must be authentication. Authenticate. If you face with any challenge during the programming, you can find the tutorial code link below this video on my YouTube channel in the description box, and then you can compare your code with mine. So now Colab asks permission to make a connection to Earth Engine account, and now actually permission granted by the user, that is me. So just click on OK and continue. Okay, done. From now on, we can use Earth Engine capabilities in the Colab environment. So, in the first step, I need to identify the region of the interest. So, make a new variable from GEE map library call map function with the base map. The base map could be satellite or any other kind of base map you're interested. Let's run. Then there is a user interface that with a satellite background allowing us to select the region of interest. Okay, now I want to select actually part of my own country for this tutorial. This tutorial not dependent to a single location or single satellite data. You can use this tutorial for all around the world, and I'm suggesting you to select your own study area for this tutorial. And let's do this procedure for your study areas and see how it works for different regions. And this tutorial will work for all kind of satellite data you have. If your data suffering from the missed pixels, this tutorial could be very useful. So, for example, in the north of Iran, we have cloudy regions. So now I'm gonna select this area. This is a coastal area, combination of forest, agricultural areas, bare land, and also the water bodies. In the next step, I need to actually have the study area as a particular variable in the code because sometimes I need to bound my satellite data to the region of interest. ROI equals to, from the map, select the draw feature. Map draw last feature, convert it to a geometry layer. To make sure, let's make a print. The ROI is created with 5 coordinate points. So there it is. The ROI settled. In the next step, we need to call the Earth observation satellite data, no matter what kind of satellites you are working. Just if you have no data, you can use for this tutorial. So, but I prefer to actually introduce one of the new collections in the Colab in the Google Earth Engine platform. I don't know if it is new or not. At least for me, it is one of the new ones. Nova Wir's NDVI product. It's an integrated product between Nova and Wir's NDVI data with daily frequency. That is one of the valuable products in the remote sensing that allowing us to real-time monitoring of vegetation cover. So Nova CDR Wir's NDVI. It is also available for LAI and photosynthetic uh, radiations. So now the NDVI is the target dataset for this tutorial and it is available since 2014 with daily frequency. It's integrated between Nova and WIRS and it has a good quality for the NDVI or vegetation related analysis. So let's copy the collection snippet and paste it for a new variable. For example, the variable name is, for example, NDVI equals to the image collection. Then select the target band. If you go to the band's description, you can find extra information about the data product. For example, there are two main bands here, NDVI and QA. So the NDVI, including the normalized difference vegetation index, useful for vegetation related analysis, but the QA bands allowing us to find the cloudy pixels or the pixels affecting by shadows. So I need these two bands, so select them, use the here through the select. The first is the NDVI and the next one is the QA. The spatial resolution is 5 kilometer and it is very beneficial for the large scale data analysis. So next, we want to actually select a year, for example, as an example for this tutorial, no matter when no matter which period you are selecting for this area. Actually, this is a tutorial and you can pick the area and also the period of time just based on your research goals. For example, I prefer to select 2020. Every year between 2014 to 2025 is okay for this tutorial. So that filter date, just like this, 2020, 2021. There it is. Let's print the NDVI and see how many images available for this period of time. So, as you can see, 366 elements available for this period, and if you collapse it, collapse the actually the band, the satellite ID here, you can see a list of satellite data available with daily frequency, all of them including two bands. One of them is NDVI and another one is the QA. And also we have some properties available here that should be considered for some of the analysis. For example, one of them is system time start that is essential for the time series data analysis. But the rest of them we can ignore it. So remember that there is a scale factor for the NDVI data that we need to apply. In the next step, I need to actually make a new function to mask out the actually the cloud and shadows based on QA band information, and then rescale the NDVI, and then try to and then go to the next steps. So let's make a new function in the new cell. A new function defined through this procedure def. A function starts with def in Python. The function name is cloud mask because the target is masking clouds. The input image considered as img, or you can pick any other name for your data, for the input data. It is optional. So first make two different variables for two different bands. We have two bands, then two variables needed. The first is the index. From input image, select the index band, NDVI here. And the next one is the QA band. From input image, select the QA band. In the next step, according to the bit mask information, we want to select the bits including the cloud and the bits including the shadow. So make a new variable as cloud. From QA band, it has a bitwise structure, so we need to actually select bits 1 and also bit 2. Throw the bitwise and from QA band dot bitwise and shifting 1 to the left by 1 bit, and then select all values but 0. The next is shadow. From QA band bitwise and 1 shifting to the left by 2 bits, and then select all values except zeros. So as you can see here, now we have a bitwise structure that selected bit 1, throw this 1 bit to the left, and bit 2, 2 bits to the left. So now the bits relevant to cloud and shadow selected, and now I need to make a single mask. Mask equals to cloud dot or shadow. So we are integrating cloud and shadow in the single image, and then actually return the values or convert the values or reverse the values through the NOT. Finally, the function returns the index or NDVI while it is masked from where all cloud covers masked from. So update mask, throw this and mask. So remember to copy the input properties for the output. We already discussed about the properties. As you remember here, each image including the properties that we need all of them, or at least the system's time start for the output. It is necessary for the extra analysis in the next step. So I want to copy the input properties to the output all the properties. For example, consider it here img.property names. img property names ensures all the properties copied and pasted to the output. So the cloud mask is a raw function. We need to apply the cloud mask on NDVI, each NDVI data. So now NDVI mask is a new variable. Bring the NDVI, apply the cloud mask on each NDVI through the map. So NDVI masked. Let's run. After a few moments, again, you will have 366 elements as expected. So, but this time, instead of two bands, only one band remained. This is the NDVI with the existing properties, because we already utilized the QA band to mask out the clouds from the NDVI image. Okay, in the next step, I'm gonna use the XEE capabilities to convert this image collection. As you can see, the satellite or time series image format in the Earth engine is the image collection, and I want to convert it to the Xarray structure, because when I convert it to the Xarray structure, I will be able to have access to numerous machine learning algorithm and a statistical algorithm locally available on Python language. So we are extending Earth Engine data actually to the Python environment for the more advanced techniques and analysis. So at the NDVI data set equals there is a new variable. Now from Xarray dot open dataset, already through the XEE, Xarray and Earth Engine combined. So from xr.open dataset, which dataset? The NDVI already masked. Engine sets to EE, and coordinate system will be EPSG 4326 WGS 84. That is same for all around the world. And a scale is pixel size. The pixel size in the EPSG 4326 is based on degree units. So 1 degree 100 kilometer. So here the data is 5 kilometer, so we need to add 0.05. This is 5 kilometer. Scale 5 stands with 50 kilometer, and there it is. This is 500 kilometer. This is 50 kilometer, for example, and this one is 5 kilometer. So there it is. The next one is geometry. The next argument sets to the ROI, because we want to actually clip our study area based on the region of interest. Let's run. And from now on, the dataset converted, the image collection converted to a Xarray structure, a multi-dimensional format. What does it mean? It means that from now on, we are out of the Earth engine and we can use the Python capabilities apart from the Earth engine for the extra analysis, for the machine learning data analysis, and extracting more and useful information. That's why I say the XEE is one of the revolutionary libraries about the Earth Engine data analysis, because it's truly expand the Earth Engine capabilities to a wider area. So here we have a multi-dimensional array structure. What does it mean? The time, longitude, and latitude, each one of them considered as a dimension, and also we have a variable as NDVI. And from now on, we should do analysis in different dimension, and we need to consider each dimensions for the analysis. So In the multidimensional array structure, now it is very easy to, for example, make a query from the satellite data and plot for a year and compare the different days together. So let's do it in the next step. In the first step, I'm gonna make a subset from the satellite data. For example, from the input data set, I'm gonna select 1 month's NDVI data to see how NDVI varies from one day to another day in my region of interest. That select the time. As you can see, we have one dimension as time. So the time equals to, from the data set, I'm gonna select the time and select months number 1. I'm gonna actually see all images for January. All images belongs to January, selecting like this. And here, let's run, and here you can see 31 image available here, and all of them related to the January. So it's very simple, and also it's very simple to do the query, to do the plots. And how to do the plots, it is also another benefit of the Xarray structure, that we can analyze the variable variations day by day or time by time. So here the variable is the subsets, or actually the new variable is a subset including the January data. The variable name is the NDVI. Let's do the plot. The plot has x, y dimension. X sets to longitude dimension. As you can see, we have longitude dimension, latitude dimension. Y sets to latitude dimension, and call sets to time dimension because we want to have a multi-temporal plot. So call wrap, I'm gonna have, for example, 8 plots in each row for the visualization. Robust sets to true to avoid missed value impact on the visualization or outlier impacts. CMap, the color map, for example, I need a color map, a palette combination of red, yellow, and green, just like that. Let's run and see the NDVI situation in the region of interest for January. So as you can see, this is the NDVI data for northern region of Iran that highly suffered from the cloud cover. Actually, it was on purpose to select an area that suffered from the cloud cover because I'm gonna actually reflect the efficiency of the suggested methodology in this tutorial for recovering the missed pixels. But something is wrong about the NDVI values. We expected NDVI between 1 and -1, but it is a big value. So the problem backs to the scale factor. As you remember, we mentioned here the NDVI has a scale factor like this that should be applied. So let's do it again. Dot multiply in the function to the scale factor, and then run a code again. Nothing changed. Just run the previous cells and run it again. Here you can see the NDVI values in the true and valid range. So now you understand what is the situation in the region of interest, and then yeah, we can also have, for example, a plot that shows how NDVI varies from one time to another time in this region. For example, imagine that I'm gonna select a point and see how NDVI values varies in this region. For example, my region of interest, as I mentioned, located in northern Iran. Here we have a croplands, and I want to actually select a point here and analyze the variations on the map to see what's the situation. When you select a point here, you have two coordinates, longitude and latitude. So a new variable as point created from, for example, from the input data, I'm gonna select a location, longitude and latitude. As you remember, we had 3 dimensions, time, lon, and lat. So the longitude is this, the longitude selected from here. Just copy and paste the latitude, the next number, This is the latitude and also the time. I'm gonna select the January image. So from the data set, selects the time. From months filter, select the month's number first. And the method should be nearest because this is a point and I'm gonna find the nearest point to this address or to this location. Let's run, and now we have a point. We have a point for a single we have a single point with values over the time for the January. So the NDVI is a variable. Select the variable name and do the plot using dot plot. So let's run, and here you can see the impact of the missed values in the NDVI data for the selected region. This is a situation when we're talking about the cloud cover and its impact on the satellite data, meaning we are dealing with a lot of missing pixels that cause a lot of uncertainties in our estimations. So before further analysis in the EO analysis, you must actually recover the missed pixels through the some machine learning or statistical analysis. In this tutorial, I'm going to show you one of the most simplest one. In the first step, I'm gonna actually do some sort of moving average technique to calculate the weekly average or the weekly maximum of NDVI for every week, and then replace the missed values with the weekly estimations. How to do this procedure? For example, now I'm gonna actually make a new image, for example, a rolling image. Why the rolling? Because the name of the function is the rolling. So the data sets, the input data set, including the no data brought here or called here, and then through the rolling function in the Python, we can actually do the moving average analysis. The time is very important. The time actually identifies the window size you want to use for the actually the averaging process. For example, if you set 7, for example, you are considering 7 days or every 7 days for the averaging or any other statistical operator, or if you consider 30, meaning that you are considering 30 days for recovering the missed pixels. So now I'm gonna actually select the 7 because I'm gonna actually the estimated values reflect the weekly changes. So the time sets to 7, mean periods sets to 1, and the center sets to true. So for each 7 days, I'm gonna get the average value. So it's optional. You can get the maximum value for every 7 days. You can get the minimum value. It's totally up to you. But typically, the average shows normal variations from the region of interest. So the rolling image is created. The rolling image, as you can see, is a Xarray image that shows the weekly uh, NDVI average for the region of interest. But as you can see in the original NDVI data, we don't want to miss the original NDVI pixels, and we only want to use the rolling image to fill the existing gaps. So that's why rolling can help us to fill the no data values. How to do this? A new variable data set field equals to the original data sets comes dot fill NA. So dot fill NA based on rolling function. Let's run. The filled dataset is created. So now the DS filled actually filled the missed pixels were missed pixels because of the cloud cover already converted to no data. So now we need to make a new subset for a new dataset for the visualization purpose. Select the dataset field and then select the time from the dataset field. So dot select the time dt dot mount sets to once. If you want to select another mount, for example, 1 should be 2. It's equals to February. So now I'm focusing on January because it's actually the most important month that's cloud cover highly affecting in the region of interest. So second subset created based on field image. So field image. Now we need to do the visualization for the new subset. Select the ndvi.plot. So x-axis longitude dimension, y-axis latitude dimension, call axis time dimension, call wrap sets to 8, and robust true to avoid missed values impact or uh, outlier impact on the quality of output. And the next one is, let's, what was that? Robust and a true call wrap. And the next one, let me to check it before. Yeah, the CMAP. Actually, I forgot the CMAP, the color palette, range of red, yellow, and green. Let's run. And now you can see most of the missed values actually filled in the new image based on the average. And remember that we only filled those pixels that was missed. And some of the images still including some missed pixels because in the input images for 1 week constantly we had, for example, no data. When, for example, you have no data for 7 days in row, so then you will have a no data in the rolling image, and the no data will reflect in the output. So if you want to actually reduce the amount of the no data, in this case, you need to increase the window size. For example, if you increase to 10 days, then the missed values reflecting 10 days change. Let's run. Definitely you will face with the lower no data pixels in the output. So there it is. Most of the no data is missed because of the actually increasing the window size. It's totally up to you again how to set the window size and the expected accuracy for your study. Now in the next, I'm gonna actually select a point for this image and do the visualization. But before going through this, let me show you how to get export from this image. So import matplotlib .pyplot as PLT. So the matplotlib allowing us to have more facilities for the visualization, including save the output. So now from the PLT save fig is a function. We can save the plot. The plot name is ndvi that is recovered with PNG format, DPI 360 and BBbox inches sets to tight. Let's run again. After a few moments, in the left panel, you will have a new image available. So there it is. Field image is available. Let's download it. And now NDVI field is available. There it is. You have a high quality layout that shows the NDVI variations, the recovered NDVI from one day to another day. Okay, now in the next step, I'm gonna show what happened after filling the gaps for the plot, for the two-dimensional plots that shows the variations. So again, point number 2 equals to from dataset recovered dataset select. Now we need to add the prior information about the coordinates. You can just copy and paste it, and sometimes also AI assistants addressing something you want to write. So this is the point number 2. Point number 2, select the NDVI and do the plot. There it is. And now you can see most of the missed values recovered here, and you can see detailed variation of the NDVI in your output image. I hope you liked this tutorial as much as I did, and try to write and test this code for your own region of interest and share your feedback on social media with other users, and try to use them in your research works. That could be really beneficial for high temporal data analysis. And please feel free to share this tutorial with other peoples who are interested to the remote sensing and Earth observation data analysis. Thank you for your attention.